This is problem 23 from chapter 17 of the textbook Stats Modeling the World, 2nd edition. Now, with this problem, it's about frogs, but 23 is a follow-on from 20. So let's talk about problem 20, or let's read the context information. So a wildlife biologist examined frogs for a genetic trait he suspects may be linked to sensitivity to industrial toxins in the environment. Okay. Previous research has established that this trait is usually found in 1 of every 8 frogs. Okay, so we have like the probability that the frog has a trait is 1 out of every 8. So obviously Q is 7 out of 8. Okay, so another thing that we could kind of look at is this is sort of a success failure situation, because frogs either have the trait or not. Okay, so let's continue. Now, so based on concerns raised by his preliminary research, the biologist in exercise 20 decides to collect and examine 150 frogs. Okay, so now n equals 150. So it's starting to look like at least a Bernoulli situation. Okay, assuming the frequency of the trait is still 1 in 8, determine the mean, mu, and the standard deviation of the number of frogs with the trait he should expect to find. Okay, so if we sort of let's say let x be the number of frogs with the trait. Okay, now if you read further, it looks like they're going to ask us, he found 22. So it looks like a binomial situation is that what we're moving towards. So here there's a question of independence. So I don't think that we can say that these frogs may be associated in some way depending on how he's sampling. So I'm not sure that we can say that there's independence, but what we can say is that the 10% rule applies, because 150 frogs is clearly less than 10% of all frogs. So that helps us justify using a binomial model. So I think it's binomial because we are interested in n or x successes in 150 trials. Okay, so with this now, with all these checks, we've justified using a binomial model, so now we can use the formula n times p to find the expected value. So that's 150 times 1 over 8, and I believe that's 18.75 frogs. And the standard deviation is NPQ, so that's 150 times 1 over 8 times 7 over 8, and we take the square root of that. So if you punch that into your calculator, you should get 4.05 frogs. Okay, so that's that part. Now, verify that he can use the normal model to approximate the distribution of the number of frogs. So I think what that's saying is that what we would like to do is draw a model, or use a model, where the center, a normal model, where the center is 18.75 and the standard deviation is 4.05 frogs. So to do that, we have two conditions. We have to check that NP is greater than or equal to 10 and NQ is greater than or equal to 10. Okay, so we already know that NP is equal to 150 times 1 out of 8 is equal to 18.75. So you need the proof. You need to actually show this. And then NQ is equal to 150 times 7 over 8, which is, I think, 131.25. And that's greater than or equal to 10. Okay? So we can use the normal model to approximate the binomial model. And we could use this notation here as well. Okay, so all we've done now is check the conditions. So now we read that the professor found 22 frogs have the trait. So x equals 22. Do you think this proves that the trait has become more common? Alright, so let's think about this for a minute. What would help us? We want to know, let's assume 22 is, I don't know where, right about here. So let's just say that this point is 22. So let me just kind of draw a line right here. We want to know how far away is that, and is that probability kind of so small that we could say that the change has something to do that's other than random sampling, because we know things are going to vary. Okay, and if 22 is not too far away from 18.75, then possibly that's what we would expect. So the question I think that we want to know is, what's this area? What's the probability? What's the probability of getting at least 22 frogs with the trait? Okay, so that we could use mathematically. We could say, what's the probability that x is greater than or equal to 22? That's what we would like to know. And so from the normal model, that is this area. What is this area? That's what we'd like to find. Okay, so we can do that now because we have the normal model. We can do this z computation. What we'd like to do is find out what's the z value here. If this is x, I should say, then what is the z value for that point? So z is x minus mu divided by sigma. We already calculated those. 22 is our number of interest. This is 18.5 and 4.05. So we get 0.8 something. 0.802. So this probability is the probability that z is greater than 0.802. And we can use the calculator, normal CDF, and we're going to go from 0.802 out to infinity, positive infinity. Okay, so 0.802 all the way out to positive infinity, which would take a long time, so we'll approximate that. And that comes out to be 0.211. Okay? So according to the normal model, we expect to get at least 22 frogs with the trait, that wasn't right, with the trait, I should say 22 frogs out of 150, about 21.1% of the time, due to natural random sampling. Okay, so that's a small number, but I don't know if it's small enough to say that this means that something else has changed. I don't know if that's enough proof. So we're just going to say that there is not enough evidence to suggest that the trait is now more common in frogs. Okay, so we're getting close, but 21% of the time it still could happen. Now I'm just kind of curious, from my own curiosity, what would it be if it was a binomial situation? We would want to know what's the probability that x is greater than or equal to 22. We used a normal model to do that. So obviously building a probability model would take quite a while, because we're going to start at 0 and go to 1, and then we're going to go out here a ways to like 20, 21, 22, 23, and then we're going to go all the way out to 150. So it's going to take, it would take a couple days to create the model. But what we're interested in is, I guess, greater than 22. We're interested in all of these probabilities here, I believe. We'd need all of those. So I'm just going to write greater than or equal to, I'm pretty sure. So this could be the probability, or this could be equal to 1 minus the probability that x is less than or equal to 21. And so that would be 1 minus binom CDF of, and we go NPX. So this would be, what would this be? This would be 150, 1 out of 8, and let's see, 21. Okay, and when I do that, I get 0.2433. Okay, so that's not quite the same. It's not quite the same as what I get from the normal model, but it's an approximation. And I think that's the point. Okay, so that's how you approach doing this problem. I hope that helped. Good luck.